Okay, this will be our homework video for section 2.5. I'm going to start with number 3. But before I can start with number 3, I'm going to have to draw the graph. So we'll draw the graph over here that's in the book. So we have a function, and it has a vertical asymptote at -1. So I'm going to go ahead and draw our vertical asymptote like this. And our function is squiggly. Then it goes like this. On the other side, we have a vertical asymptote at 2. Such as that. And now our graph comes over here through the origin and up like this. And then it comes down and it has a horizontal asymptote on this side at 1. So our graph comes down, passes through the horizontal asymptote, which is completely allowed. We learned that in pre-calc, and it goes this way. And then over here, we have another horizontal asymptote, and this one looks like it's at 2. So then they ask us several questions about this function in terms of limits. Part A says, what is the limit as x approaches 2 of f of x? So here's 2. We put our bead on the string. So as we get closer to 2, from the right-hand side, we're going to infinity. On the left-hand side, we're also going to positive infinity. So we would say the limit here is positive infinity. Part B says, what's the limit as x approaches -1? Now, these are both two-sided limits. So we have to, oh, this one, I apologize. This is a one-sided limit. It's from the left, right? It's from the left. So what's the limit as x approaches -1 from the left? As we approach from the left or below, right? We're coming from this direction, from the left or below. As we approach, our beads go to positive infinity because our function goes up at that vertical asymptote. So this would be positive infinity. C says, what's the limit as x approaches -1 from above of f of x? Now, as we approach -1 from above or from the right, we're coming from this direction towards -1. Our beads would be on this part of our function. And so that's going to negative infinity. Now, they don't ask us in this problem, but if they were to ask us about the limit as x approaches -1, not the one-sided limits, but the two-sided limits, we would have to say it fails to exist because from this side it goes to positive infinity, this side it goes to negative infinity. Part D says, what's the limit as x goes to positive infinity? Now that means x, our x value, our domain value, is going to grow without bound. So this is x. X is growing without bound. And as x grows without bound, our beads would be on this part of the graph, and they get closer and closer and closer to +1. That's our horizontal asymptote. Please note that our function crossed through the horizontal asymptote. I mentioned that when I was drawing this. That's completely allowed. Functions can cross horizontal asymptotes. Over here, it crosses it an infinite number of times. Part E says, what is the limit as x approaches negative infinity of f of x? And as we approach negative infinity, right, x is getting smaller and smaller without bound, our function oscillates around the line, back and forth across the line, y equals 2. So that's our horizontal asymptote. And then it says, part F says, write the equations of the asymptotes. Well, we have 2 vertical asymptotes. The first one is, so under the vertical asymptote, we have x equals -1. That's our vertical line. We have x equals 2, our other vertical line. And then for horizontal asymptotes, we have y equals +1, and we have y equals +2. Okay. So that's number 3. Let me erase this. So let's take a look now. The next part of the homework is 7, 8, and 10. And these questions say, sketch a graph of a function that satisfies the given conditions. So I'll do number 8 here. They're all the same. 7, 8, and 10 are going to be the same. So 8 gives us a set of conditions. It says the first condition is the limit as x approaches 3 from the right of our function has to equal -infinity. Okay, so that's our first condition. Then it says the limit as x approaches 3 from the left of our function has to equal +infinity. And finally, it says, well, this isn't the last condition, I apologize. The limit as x approaches infinity of f of x equals infinity. And then the last condition is f is odd. Now we need to remember that an odd function has origin symmetry. Right? That's what it means to be odd. An odd function, something like f of x equals x cubed, right? That's a simple odd function. That function looks like this. It has origin symmetry. So our function has origin symmetry. So when we draw our graph, whatever we get on the right-hand side of the y-axis, we're going to have to duplicate that on the left-hand side of the y-axis. So what do they tell us? Well, first they tell us that as x approaches 3 from the right, we go to -infinity. As x approaches 3 from the left, we go to +infinity. So at 3, we have a vertical asymptote. Now, because we have origin symmetry, we would also have a vertical asymptote at -3. Remember, origin symmetry, same function, symmetric with respect to the origin. Now, as x approaches 3 from below, from above, we'll do the first one first. As x approaches 3 from above, that means as we approach 3 from the right-hand side, our graph is going to -infinity. So we can make our graph. So it's going to -infinity from this side, okay, like that. As x approaches 3 from below, from the left, as we approach 3 from the left, we're going to +infinity. So our graph is going like this. Now, we don't know anything else about the rest of the graph, but it does say here, as x approaches infinity, as x grows without bound, our function grows without bound. It goes to infinity. So this part of the graph is going up without bound. Now, from here, we can use our origin symmetry, the fact that our function is odd, and we can reproduce this graph with origin symmetry on this side. So if we're symmetric with respect to the origin, this is going to +infinity. When we reflect that through the origin, we would be going to -infinity. So we can make our graph look like whatever we want it to look like, but it has to be symmetric. So let's just make our graph do something like this. And so we have our origin symmetry there. And now over here, as we approach x from above, we're going to -infinity. So over here, as we approach x from below, we're going to have to go to +infinity. So this function is going to be going this way. And then we need to keep the symmetry here. So we would have it go something like this. So this is our function. Again, the fact that they told us the function is odd, origin symmetry, that allows us to draw the other half of the graph without them having to give us all that information in terms of limits. So that's number 8. 7 and 10, similar problems. Okay, similar problems. Try those on your own. From here, we get a problem like number 11. It says, guess the value of the limit, right? They want us to take a swing at this problem. It has a little red symbol next to it. It has a little graph on it. That means they expect you to use your calculator to work this problem out. So number 11 says, what happens if we take the limit as x goes to infinity of x squared over 2 to the x? Okay? And they want us to guess. They want us to guess this. And they say by evaluating the function when x is 0, x is 1, x is 2, x is 3. And then there's a comma, 4, 5, 6, 7, 8, all the way up to 50 and then 100. Then use a graph of f to support your guess. So what do they expect us to do? Well, they want us just to work this out with our calculator. They want us to plug numbers in and see what's going to happen. But let's, you and I, just have a conversation without the calculator. Let's have a conversation about this. Let's look at this from, and let's just analyze this. We'll just take a look and see what's going on here. We have a quotient. Our numerator is x squared. Our denominator is 2x. Now, if we think about this, what we say in math, we say, does one of these functions dominate the other? Right? Dominate the other, meaning does one grow faster than the other? If the numerator grows faster than the denominator, then the numerator is going to get bigger and bigger and bigger and bigger and bigger, and the denominator is not going to keep up. So the numerator is going to get really huge. The denominator is going to peter along, growing, but not nearly as fast. And so this quotient will head for positive infinity. Now, reverse that. Think about it the other way. What happens if the numerator grows slower than the denominator? Then the denominator becomes huge, right? It will become huge. The numerator is slower, i.e. smaller. And if the denominator is huge and the numerator is smaller, and it keeps getting bigger in the denominator over and over and over again, then this is going to approach 0. This is what they want us to investigate. They want us to investigate which of these functions is going to grow faster. I mean, if we just think about these two functions, right? If we just think about f of x equals x squared, and well, we'll call it g of x, so it's not confusing. G of x equals 2 to the x. Let's just plug some numbers, right? If we plug in 2, this gives us 4. This gives us 4, right? So that's a tie. That means that would be a 4 and that would be a 4. We get a ratio of 1, but we're going to infinity, not 2. So we'll plug in a bigger number. We'll plug in, now they want us to plug in a bunch of numbers over here. So we'll just plug in 3, right? 3 squared is 9. 2 to the third, 2 to the third, 2 times 2 times 2, 2 to the third, that's 8. Okay. What about 4? Well, 4 squared is 16. 2 to the fourth, right? 2 times 2, 4 times 2, 8 times 2, 16. What about 5? 5 squared is 25. 2 to the fifth is 32. So we had a tie here, we had a tie, right? Over here, this one was bigger, so we'll point the arrow that way. Over here, we had a tie again. This one is bigger, so we'll point the arrow that way. Over here, this one is bigger. Now, what about 10? Right? What about 10? We'll just skip down to 10. 10 squared is only 100, right? It's only 100. But what's 2 to the 10? 2 to the 10 Well, 32 is 2 to the 5th, right? So 2 to the 10th is 2 to the 5th squared, power to a power you multiply. That means this is 32 squared. Well, 32 squared is way bigger than 100, right? So this one, we'll make a really big arrow. This one is massively bigger than this. And if we put in a number like 100 squared, that's only 10,000. Right? Square, you get 4 zeros. Over here, you get 2 to the 100th. Well, 2 to the 100th, right? 2 to the 100th is 2 to the 10th to the 10th. Power to a power you multiply. But we just said 2 to the 10th was 32 squared, right? 2 to the 10th is 32 squared. So that's 32 squared to the 10th. That's 32 to the 20th. 32 times 32 times 32 times 32, 20 times. That's massively larger than 10,000. So we can see, just plugging these numbers in, which is what they want us to do here, we can see that this function dominates. It dominates. It gets bigger much faster than x squared. So if the denominator is growing faster than the numerator, then this is going to equal 0. So this is the kind of analysis they want us to do in a calculus class. Right? So in this case, it's just an investigation of these two graphs or these two functions. If you think about the two functions, right? If we just draw them sloppily, a lot of us go, well, you know, this is a parabola. Here it is here. And this is 2 to the x. And it goes like this. Well, okay, that's true. That's the rough sketch of both of those. But in reality, right, this, as we just saw, by the time we look at this graph goes much steeper. Right? Much steeper than this graph. That's what we just said. This y value is all the way up to 32 to the 20th. This y value is only at 10,000. I know 10,000 is a big number, but relative to 32 to the 20th, 10,000 is not a very big number. Right? So that's a very interesting problem in problem number 11. So now we get down to 15, 16, 17, 18, 19. And it says find the limits, right? Find the limits. So let's take a look at number 16. 16 says the limit as x approaches -3 from below of x plus 2 over x plus 3. Now we can't just plug this in, right? If we just plug in -3, if we go with our step of just plugging it in, then that's going to give us 0 on the bottom. And that's not what they want us to do. They don't want us to say undefined, fails to exist. They want us to tell them, if we look at a graph of this function, if we just had this in pre-calc, all of us remember from pre-calc that this graph has a vertical asymptote at -3. What they want us to tell them is, as we approach -3 from below, right, from this side, are we going down, 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 down like this, because we know it has vertical asymptote, or are we going up, 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 up like this? This is the question. Now we can answer this in pre-calc. In pre-calc, they asked us to graph rational functions, and when we graphed the rational function, we had to come to a conclusion as to whether the graph went down at the vertical asymptote or up at the vertical asymptote. So we could do this in pre-calc. Right? This is a pre-calc approach. And now in pre-calc, we didn't say anything about the limit. We just said we're going to graph this. And what did you and I do? We plugged in numbers. So we did. We plugged in numbers and asked ourselves, what's happening? Now, if you were in my pre-calc class, what I told you to do was, well, we're investigating from the left-hand side, right? Minus the left-hand side. We're investigating from this side. So my suggestion to you was to plug this number in right here. Plug a number in, see what happens. See if you get a positive number or a negative number. If you get a positive number, you're going up. If you get a negative number, you're going down. That would have been my suggestion if I was your pre-calc teacher. Now we know what a number really close to that is. A number really close to that, right? We could use negative 3.001, something like that, right? We'll use that. Now what happens when we plug it into our quotient? We plug it into our quotient, we get negative 3.001 plus 2. We get negative 3.001 plus 3. Now, really, all we want to know is it positive or is it negative? That's what we want to know. If it's positive, it's going up. If it's negative, it's going down. We can simplify this to its most basic approach if we understand that this function has a vertical asymptote of 3. Now, when we take negative 3.001 plus 2, we're going to get negative 1.001. We get a negative number on the top. When we take negative 3 plus negative 3.001 plus 3, we're going to get negative 0.001 on the bottom. The important thing here is we get a negative divided by a negative. This is equal to a positive. Well, if it's equal to a positive, we're going to positive infinity. Again, this is the kind of analysis they expect us to be able to work out based on our pre-calculus experience. This is the kind of analysis in a calculus class that we need to fall back on to work out problems such as this. All right, what about something like 17? Well, maybe 17 is a little more frightening because it has an exponential function. Now, exponential functions are not supposed to be frightening to us, but it's okay. We're not supposed to be scared of a lot of things in life. I mean, there's a lot of things in life that are a lot more frightening than something we find in our math book. So 17 says, what's going on with the limit as x approaches 2 from the right? And then they give us a convoluted function. They give us e to the 3 over 2 minus x. Excuse me. So what happens when we plug in 2 from the right? Okay. So here we are on the graph. We're at 1, 2, right? We're coming to 2 from this way. Again, my suggestion to you, if you were in my pre-calc class and we were trying to graph this, we didn't know about limits then, we're just trying to graph this, would be to pick a number. You're coming from the right, so pick a number right here. We would use x equals 2.001, something like that. And ask ourselves, what happens over here if I plug that in? Well, what does happen, right? I get e to the 3 divided by 2 minus 2.001, which is going to be e to the 3 divided by 2 minus this is going to be minus 0.001. Now 3 divided by minus 0.001 is 3,000, but this is going to be e. There's going to be a 3,000 here, but we have a negative sign. So what does this look like? This is 1 over e to the 3,000, right? Because a negative exponent means we write the reciprocal. Well, 1 over e to the 3,000 is 1 over a huge number. I don't know what e to the 3,000 is, but I know it's massive. And 1 divided by a massive number is 0. So this limit equals 0. So for a lot of people, these kind of problems, right, where you get to do this analytical kind of reasoning exercise, a lot of people really enjoy these. It's like, oh, I'm using all the things I learned in pre-calc and I'm putting together with my calculus and I'm investigating functions. In pre-calc, we just called this finding vertical asymptotes. In calculus, we call this, evaluating limits involving infinity. Turns out they're the same thing. And what about something like, 19? It involves a log, so let's take a look at that one. All right. 19 says we have the limit as x approaches 3 from the right of the natural log of x squared minus 9. And again, on a graph, 1, 2, 3, we're approaching 3 from the right. We're coming in this way. So mentally, we're going to pick a number right here, like x equals 3.001 again. Now, what does this look like? I don't know. Let's plug it in. What is the natural log of 3.001 squared minus 9? Right, that's what we're asking ourselves. And again, we don't need to grab our calculator and get the exact answer here. We know that if we square this, right, we're going to get this number right here. It's going to be barely bigger than 9, right? It's going to be 9-ish. Right? It's going to be barely bigger than 9. When we square that number, we're going to get a 9 here. We're going to get this. We're going to get a number barely bigger than 9. Minus 9, this is going to equal the natural log of a tiny positive number. Now, we're supposed to know the graph of the natural log, right? That's one of those graphs we're supposed to know. Without thinking, we're supposed to know that the graph of the natural log goes like this. Now, what happens if we take the natural log of a tiny positive number? Well, now we're right here, right? Because we're coming this way, we're going tiny positive, really close to 0, but positive. And so our graph is going to negative infinity. All right? See, these are a lot of fun. From here, they ask us to do 21 through 27, right? So not every one of these problems can we just algebraically unpack and solve. Some of them we have to analytically approach, just kind of reason our way through the behavior of the functions, falling back on our pre-calc knowledge, or expanding our pre-calc knowledge as we move through the calculus class. So let's take a look. If we look at like 24, for example, all right, 24. We'll start with 23. We'll do 23, and then we'll branch out to 24. This is the limit as x approaches infinity of x cubed plus 5x divided by 2x cubed minus x squared plus 4. Now, we talked about a problem similar to this in class on Wednesday, and we said, okay, if we have a rational function such as this, polynomial divided by polynomial, our approach is to divide the top and the bottom by the highest power of the x term in the denominator, right? So we're going to rewrite this. This is x cubed, so we're going to take x cubed divided by x cubed plus 5x divided by x cubed. Then we get 2x cubed divided by x cubed minus x squared divided by x cubed plus 4 divided by x cubed. So we find the highest power of x in the denominator. We divide every term by that. Now, what is this going to look like? When we simplify this, and we can simplify it, it's important for us to realize that we can simplify it because x is going to infinity. So x is not 0 because 0 doesn't live near infinity. X cubed divided by x cubed just gives us a 1. 5x divided by x cubed gives me a 5 divided by x squared. X cubed divided by x cubed gives me a 2. X squared divided by x cubed gives me 1 over x. 4 over x cubed just turns out to be 4 over x cubed. And now we ask ourselves, what's happening as x grows without bound? And this is that idea that we investigated in problem 11. That's why we had problem 11, so we could get to a problem like this and work it out using mental math instead of just calculating in our calculator. As x gets really, really big, 5 stays 5. But when x gets really, really big, this denominator grows without bound. If x is 100, which is nowhere near infinity, this is 5 divided by 10,000. That's a tiny number. If x is 1,000,000, 10 to the 6th, this is 5 divided by 10 to the 12th. And 1,000,000 is nowhere near infinity. So this is approaching 0. Similarly, this function, x, dominates this constant function. So this goes to 0. This term also goes to 0. And we're left with the limit of a constant, which is the constant, and the limit of the constant, which is the constant, and this function goes to 1/2. Now, what does that mean? Well, we said limits as x goes to infinity. We said that's a horizontal asymptote. So this function has a horizontal asymptote as we go towards infinity. And I don't know what the graph of the function looks like, but I do know that as this graph goes this way, either from below or from above, we didn't do any analysis, so we don't know which way it goes, but somehow as x grows without bound, this function, either from below or from above, it gets closer and closer to 1/2. That's what this limit tells us. Okay, so that's 23. Now, what about 26, right? 26 is a little different. There's an example. I don't think there's an example in the book on how to do 27, but there is an example. There is not an example on what to think about with 26. So let's take a look at 26. 26 says, what's the limit as x goes to infinity of x plus 2 divided by the square root of 9x squared plus 1. Now we have to do a little thinking on this one. This one we're going to have to do a little bit of thinking about before we can come up with the answer. Because again, we're going to focus on the denominator. The highest power of x in the denominator is right here. That's x squared. However, it's under a radical, right? It's under a radical. So what we have in essence there is we have the square root of x squared. We don't really care about the 9. We're just looking at the function. X is going to infinity. The 9 is going to be 9. The x squared is what's growing, but it's under a radical. See, that's the little hitch in the giddy up here. And we know, based on what we talked about in class, that this equals the absolute value of x. The absolute value of x, which means I can replace it with x if x is greater than or equal to 0, and I can replace it with the opposite of x if x is less than 0, right? That's what this problem is checking. This problem, yes, it's about limits as we approach infinity, but it's also, does the student remember the square root of x squared is not x? So when you have a square and a square root, a cube and a cube root, not a big deal, because the cube root of x cubed is just x. It's the even roots where we have to do this piecewise defined function. So what does that mean to us? Well, it means x is going to positive infinity. If x is going to positive infinity, this is us right here. This is us. So when we rewrite this, down here, we're going to divide by the highest power of x in the denominator. So we're going to stay under the radical. We're going to divide everybody by x squared. But in the numerator, where we're not under the radical, we have to, algebra says you have to divide the denominator and the numerator by exactly the same value, right? We got to divide by exactly the same value. Down here, you're dividing by x squared under a square root. So in the numerator, you're going to have to divide by the equivalent term. The equivalent term. The equivalent term to x squared under a radical is either going to be x or the opposite of x. And we decided, because we're going to positive infinity, we're equivalent to positive x. So we have to remember up here to divide by x to the first power, because our squared is under a radical. So what does this work out to be? Well, if we do a little bit of math, right, we get the limit here as x approaches infinity, x divided by x, 1. Again, they can cancel because 0 is nowhere near infinity. 2 over x is going to be 2 over x. That doesn't simplify. Down here under a radical, x squared cancels x squared. We get a 9. Here we get 1 over x squared. Now we use our dominating function idea again. As x grows without bound, 2 divided by x goes to 0. 1 divided by x squared goes to 0. And we're left with the limit of a constant divided by a constant. Don't forget to take the square root here. And so we get 1 over 3. Now, there isn't a problem in your homework. That doesn't mean there won't be a problem in the chapter review. Real quick, if this problem had been written instead of positive infinity, for all you watching the video here, you're getting a bonus lesson here. If it had been written to negative infinity, right? If instead of positive infinity, this had gone to negative infinity, well, then when we come over here, x is going to negative infinity. X is clearly less than 0. This is what we would be replacing by. In other words, this would be a minus x. This would be a minus x. When we came down here, x divided by negative x would give us a negative 1. And now we would have negative 1 over 9, and we would get negative 1/3. Okay, so problem 27, there's an example in the book showing you exactly how to do problem 27. So I'm not going to work that one out. What about 31, 32, 33, those kind of problems? Same idea there. Does one function dominate the other function? Same idea. Let's take a look at 31 is just cosine, right? We know what cosine does. I mean, we can do 31 really fast. It says as x goes to infinity, the graph of cosine goes like this. Well, that doesn't have a limit. It fluctuates between -1 and 1 and all the numbers in between. So we would say fails to exist, right? It doesn't go to positive infinity. It doesn't grow without bound. It doesn't go to negative infinity. It doesn't have a horizontal asymptote, so it just fails to exist. What about 32? This is the limit as x approaches infinity of sine squared x divided by x squared. Now, in pre-calc or trig, wherever you met trig for the first time, we said sine squared means sine x squared. And this is x squared. Now, this is another one of those dominating idea kind of graphs. Does one function dominate the other? Well, what do we know looking at these two graphs? We know this function right here is always between -1 and 1, right? If we plug any number into sine going to infinity, sine, the graph of sine, right? Well, we've got cosine drawn there, so we'll draw sine over here just to be fair. Sine goes like this, and we're always going to get a number between 1 and -1, always. That's what we get. Now we're squaring it. We're squaring it. So the negative becomes positive. So in essence, we're really always getting a number between 0 and 1. The biggest the numerator is ever going to be is 1. The smallest it's ever going to be is 0. This is the analysis part, right? This is the analysis part of our pre-calculus class that they want us to bring to our calculus class. What happens in the denominator, however? Well, the graph of x squared, we know that's a parabola. It goes like this. It grows without bound. So the numerator is always bounded between 0 and 1. But the denominator is growing without bound. I don't know what my numerator is, but I know it's no bigger than 1 and it's no smaller than 0. It's always between 0 and 1. But the denominator is huge. The denominator grows without bound. If I have a numerator that's constant, I don't know its value, but it's a number between 0 and 1. And I have a denominator that's growing without bound. This goes to 0, right? It's 0 between 0 and 1 in the numerator. The bottom, right? The bottom is heading to infinity. So I have a number divided by infinity. I'm going to get 0. What about something like 34? The limit as x approaches infinity of e to the 3x minus e to the minus 3x divided by e to the 3x plus e to the minus 3x. Can we do the same thing we did before on this problem? Can we ask ourselves, what's happening? Can I divide by the highest power of x in the denominator? Well, let's take a look and see what we have here. This is the limit as x approaches infinity of e to the 3x minus e to the 3x is just that. E to the minus 3x, though, is 1 over e to the 3x, right? That's what that negative exponent means. We write the reciprocal. This is e to the 3x right here, plus 1 over e to the 3x like this. Now, let's just ask ourselves, as x grows without bound, this is 1 divided by e to the infinity. E is 2.781828182845.9, and it goes on forever. It doesn't repeat. Somebody forgot to silence their cell phone while making a video. So this goes to 0. This also goes to 0. And what does that leave us? That leaves us the limit as x goes to infinity of e to the 3x over e to the 3x. Well, the order of operations say we do the quotient before we do the limit. E to the 3x divided by e to the 3x is 1. So this is the limit as x goes to infinity of 1, and the limit of a constant equals the constant. So problem 34 is 1. All right. So where do we go from here? Well, problem 39 through 42 says find the horizontal and vertical asymptotes of each curve. If you have a graphing device, check your work by graphing the curve and estimating the asymptotes. Okay, so let's do one of those, right? We'll do one of those. And that'll give you an idea how to do the other two. One of them is no more difficult or no more illustrative of the technique than the others. They're all similar problems, similar in difficulty, similar in approach. So I'll pick 40. I'll pick 41. Or we can pick 40. We'll pick 41. We'll talk about 42 real quick because I'm sure a lot of you aren't happy about the e to the x. So let's take a look at 41. What do we have here? We have y equals x cubed minus x divided by x squared minus 6x plus 5. Now, if we factor that, that's what they taught us to do in pre-calc when looking for asymptotes. That's going to be x times x squared minus 1. This is going to be x minus 5 times x minus 1. Or that's going to be x times x plus 1, difference of two squares, x minus 1 over x minus 5, x minus 1. All right. Now we have to be careful here, right? We got to go back to our algebra 2, our pre-calc, and we have to realize that just because when is our denominator 0? Right? For a lot of us, that's where we have our vertical asymptotes. But you can't just arbitrarily set the denominator equal to 0. In this problem, what Stewart is trying to get us to see is you can't take the denominator, set it equal to 0, and say, there are my vertical asymptotes. That's the incorrect approach. Because here, this cancels this, right? Linear term cancels linear term. We have a hole at x equals positive 1. We don't have a vertical asymptote there. It's the simplified version of your rational function that you utilize to find your vertical asymptotes. Simplified, right? Simplified. So in your denominator, you always have to simplify first. If you don't do that, you think there are two vertical asymptotes when in fact there's only one. Now our denominator is x minus 5. We set that equal to 0 and we get x equals 5 is our only vertical asymptote. This is not a vertical asymptote. This is a hole. Now, how do we find horizontal asymptotes, right? Well, horizontal asymptotes, we consider the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. That's what we do. Now we know how to do those, right? We know those are a mechanical process when you have a rational function such as this. We take the mechanical approach. We rewrite this as the limit as x approaches infinity. We're going to write this as x cubed over x squared, right? Because we divide everybody by the highest power of x in the denominator, minus x over x squared, divided by x squared, divided by x squared, minus 6x divided by x squared, plus 5 divided by x squared. We then simplify. Here we're left with x. Here we have minus 1 over x. Here we have 1. Here we have minus 6 over x. And this is 5 over x squared. Now we've seen problems similar to this prior to this problem in the homework. We know this goes to 0. We know this goes to 0. And we know this goes to 0 by our dominating function analysis idea. But what are we left with? We're left with a limit as x approaches infinity of x divided by 1, or the limit as x approaches infinity of just x. Now, what does that turn into? Well, that's obviously infinity. So we do not have a horizontal asymptote at positive infinity. What about if we take the limit as x approaches negative infinity? Well, we would do the same exercise here. We would divide everybody by x squared. because it's x squared and we're going to negative infinity, we're going to square it. It's going to stay positive. So we don't have any negative sign analysis to work in here. And what do we find out? We would get right back to this step right here. This step would be right down here. And we would end up with this, which would be negative infinity. And so if we wanted to draw the graph of this function, which I don't believe in problem 41, they even ask you to do it. It says, if you have a graphing device, check your work by graphing. If we wanted to draw the graph of this function, we could. We can now draw the graph. We have everything we need to draw the graph. We know that there's a vertical asymptote of 5. We know our function as x grows without bound. Our function grows without bound. So we know our function is going to infinity over here. We know as x goes to negative infinity, our function is going to negative infinity. So our function goes down this way over here. We don't have any horizontal asymptotes. We know there's a hole at x is 1. At x is 1. Now, I don't know where this hole lives, but somewhere on this vertical line right here, there's a hole. Now that's not an asymptote. That's why I'm making it an orange. There's a hole there. How am I going to find it? Well, you have the simplified version. Simplified version is right here. Go plug in 1. What do you get? You get 1. 1 plus 1 is 2. 1 times 2 is 2. Down here you get 1 minus 5, negative 4. So we have 2 on the top, negative 4 on the bottom. We have negative 1/2. So our hole is right there at negative 1/2. There's our hole. Now we can draw the graph. We know what happens when we plug in 0. When you plug in 0, you get 0 times 1. That's 0. When you plug in 0 here, you get 0 minus 5. So you get 0 divided by negative 5. That's 0. So our graph goes through this point. It also, from right here, has a 0 at 1, negative 1, pardon me, has a 0 at negative 1. So right here at negative 1, we have another 0. And in pre-calc, going back to pre-calc again, they told us if the power of that was odd, like it is here, power's 1, that's an odd number, the graph is going to pass through those 2 points. Now that makes sense, right? Because we have a hole here, the graph's going to touch this. Now that's a 0, so it has to touch that. Now, if it just bounced off, but it doesn't, it passes through, and it goes to negative infinity. It says so right there. So this is what our graph looks like. Now over here it goes to positive infinity. We don't know what it's doing on either side of that asymptote. We can find out, right? We can find out in a calculus class. We would find out by going, well, what's the limit as x approaches 5 from above of f of x? And what's the limit as x approaches 5 from below of f of x? We take the one-sided limits. We put the bead on the string. We ask ourselves, well, what's a number close to 5 but bigger? Well, we've done this in class today. That's like 5.00001. So we plug that in. How do we plug that in? That would be 5.001 times 6.001, because we add 1. Down here we have 5.001 minus 5. So what do we get? It's positive. Positive, positive, positive. It's positive. The denominator is tiny, numerator is big. Denominator is tiny, numerator is huge. That number is going to be big. So we're going up on this side, which we already knew. If you think through this, you were already aware of that. Look, you're going up. What are your choices? Up or down? Those are your 2 choices. But to go down, you would need a root. You don't have any more roots. So the only thing that can happen here is the function goes like this. And what happens on the other side? We'll plug in a number like that, 4.99. So we have 4.999 plus 1 is 5.999. positive and positive, but down here we have 4.9999 minus 5, negative, which means it has to go down. But we already knew that. Look where our hole is. It has to go down because if it decided to go up, it would have to cross the x-axis, i.e., it would need another root. We don't have another. There's our graph. We don't need a graphing device to graph that. We just need our analysis skills that were taught to us in our pre-calc class. We mix those in with our calculus ideas. We could, this problem right here is a pre-calc question. Graphing this is a pre-calc question. Many of you did that in your pre-calc class. You didn't know any calculus, and you could draw that graph. All we've done in a calculus class is told you that the horizontal asymptotes, which you searched for in pre-calc, are actually limits. And we've told you the vertical asymptotes, which you searched for in pre-calc, are also limits. That's the big idea in section 2.5. All right, I hope this helped.